Oh, oh no.
Whoa.
Oh, hello.
Nailed it.
Oh.
Hope you're getting this on record. Okay, this board's annoying already.
So,
Whoa. All right, I thought you saw me walk by.
no.
No, the board's a bit broke.
Okay.
I mean, when it was upside down, I could do something. But when it changes from upside down to upside up
You have to
and
just
back
keep doing it
again
quickly.
20 times a second, then I don't think I can do anything.
Oh my god.
Okay, I think it's stabilized upside down.
Nope.
That's really nice. Okay, so I think I'm going to record. Anyway, this is well, that's okay. I mean,
This, like, yeah, take back his camera and like, oh, look what it's doing!
I think it's stopped now. Oh,
No. It'll be something to do with the wires at the back.
I don't know.
or at the front,
Loose.
or with the one. Oh, yeah. But
Or it's just not bad.
Yeah, there is a projector.
You can almost read that table. The table actually doesn't move. That one in the middle.
Really?
Bristol Brown.
and it just transposes, isn't it? So so that's okay. Right.
You have to handwrite it all afterwards.
So presumably, everybody knows what this exercise is about. Because
Yeah, it's.
the only problem is with that Neil wasn't here last week, I think. No, oh, you're
Don't worry, there's really not much we can do.
Oh, it flashed to the right side of it.
Helen, it's been alternating every couple of seconds.
This is awesome.
Well, it's flashing, surely it's a leak.
That's what I said.
But it didn't start flashing until about
Oh, if I freeze it, when it happens to be, but it doesn't happen to be.
just wait for it to go. Try and time
Yes,
it.
well, I'm waiting for it to go. But it's not trying, it's not going anywhere.
It's stabilized.
Broke it now.
Watch, right, watch the angle, turn it upside down, and then it'll come back.
Yay, close enough.
I move it left, it moves right. Which I suppose is, I move it down, it moves up.
No, it's not.
Okay, this exercise is a bit of a, this is the last, I think this is, to finish off that huge part of what we've been doing, IOP formulations and things like that of various problems, and this one was a bit of a challenge. So I don't know if anybody's attempted it, but if you haven't, then in German they say selber schuld. Well, to your own peril.
Google Translate.
Okay, what's the question? The question is, looks completely new to everyone. The question is, you've got a company with various departments, and these departments need to be relocated. Some of them can stay in London, some of them have to move to, well, some of them can move to Bristol, and some of them can move to Brighton. And there are some constraints, and there are some costs. So one of the constraints is that something has to relocate, because here it says that none of the cities may be the location of more than 3 of the departments, and there are 5 altogether, so at least 2 of them have to move out of London. And yeah, and there are some benefits from relocation, because there are lower rents and I don't know what. It says that it's not. Gives you some ideas. So for example, if you move department D to Bristol from London, you get a saving of £20,000 a year. But then there are some costs related to relocation. So if you have, for example, so if you move D to Bristol and A stays in London, they communicate. If only
It was upside down.
if it doesn't respect my freeze, then I'm good. Yeah, so you get 1.5 thousand times what is the cost of communication between Bristol and London? 13. Okay, so if you only move D and A stays in London, then what you get is 13,000 times 1.5 cost.
6,500.
I think it's 19,500.
1.5.
Oh, I thought it was 1.5 times 13.
Yeah, it
Yes.
is.
That's
You just did
19.5.
5
Oh.
times 13.
Yeah, I did 0.5, didn't I? Oops.
Yes. So you wouldn't gain so much. Okay, that's the idea of this exercise. Now I think I'll switch to I'll switch here for us to solve it, because otherwise I wanted to do it on paper, but somehow it doesn't seem such a good idea anymore.
Is this one called decentralization? Yeah.
Yes,
Yes.
it's called decentralization. I've given you not any room. What do you mean? Ah. Use your own room.
See this, but they're not losing all.
Yes, but I know you always carry a stapler
know.
to my lessons. Okay, so it's the model here. I mean, it's very suggestive that we should use something similar to the lecture just before the homework, right? But if it wasn't given as an homework exercise, then you'd probably have to think about what kind of model to apply. But in this case, it's a mixed integer, or even integer, or MIP, yeah, if you want. Model. So there will be, actually, it's not mixed at all, is it? Yeah, it's not mixed, so it's just an integer linear programming model. And has anybody attempted at all?
Sorry, yeah.
No? Are you sure? Okay, that's a shame.
At least we are
Yes, yes.
always the best policy.
Okay, so I'll read the book also that was cited at the beginning of the question has the solution. So that was one way of solving it. But of course, that's not the most useful way, just reading solutions. So, but I have a copy here of their solution. So I'll follow that, but it's kind of clear. So this will be a 0-1 decision variable, which is going to be 1 if department I moves to city J. Okay, and 0 otherwise. And I, of course, goes through all the departments, so A, B, C, D, E, and J is London or Bristol or Brighton. Okay, so S is Bristol. And G is Brighton. What exactly? I've not skipped anything anywhere this time.
Doesn't name something hash like that.
I'm literally taking it from the book. I didn't change anything on that example. So, including the notation S for Bristol and G for Brighton. So don't blame me for everything. But the problem with this is that you have to. What? Is J.C. Forbes a plagiarist? No, this is not J.C. Forbes' book. This is Will H.B. Williams's book.
I think that makes it even worse.
And it's cited, and I'm only using 2 pages, which I'm allowed under the Crown Copyright and Police Enforcement Act 2017, as yet to be passed by Parliament. And don't ask God for help. God's not going to help you. Okay, this is not everything. The problem with this is that you need to know, so there are these costs. If this department is in London and that department is in Brighton, then there is some cost of that communication. Right?
Carry on, sorry.
And so that communication, you don't have the questions. So this is my copy. Okay, send it back then. Okay, so this communication, you need a 0-1 switch, whether you're incurring that cost or not. So you need another set of decision variables, gamma ij, they call it KL. Okay. For I less than K, well, A is less than B, and so on. And where the cost, where the communication amount, now I haven't got the question.
Sorry.
That's okay, no.
Sure.
You froze the screen.
Froze the screen. Oh, I froze the screen. So I could, when I need something, I could look. No, that thing is off now.
Oh, that's a good issue.
Okay, so where CIK was non-zero, so the amount now it's off. Okay, the CIK was the quantities of communication from the second table between the department I and department K. Okay, and then and this is going to be 1 if what? So what we want is if department I is in J and department K is in L. Okay, so if and this should be equal to 0, otherwise. Okay, so this expresses reality, possible reality in the solution that I put department I to J and department K to L, and then it's 1, and then I need to add the cost of the communication between department I and department K, and the amount of the cost is if one of them is in J and the other in L. And this is what's given in the 2 tables, CIK, DJL at the bottom. So this is what enters the objective. So the objective is to maximize the gain. Oh, it doesn't have the objective. Or minimize the cost. It's up to you. So we can say it's to maximize. Okay, so what was the gain? The gain was given in the top table. And I'll call it Bij over all I and j in the sets that where they come from, times delta ij. Okay, so Bij is the benefit of relocating department I to location J. So that's the table 1. It's the first table in the question. And take away the cost of all the communication. So the cost of communication is CIK is the amount of communication between I and K, and DJL is the cost of communication between city J and city L per unit. Okay, and this cost is incurred if I goes to J and K goes to L. Does that make any sense?
Mm-hmm.
I, J, K, L. The sum is over all the possible 4 tuples of I, J, K, and L, with the obvious sets as the ranges. And yeah, I is less than K. So we don't count it twice between the 2 departments. Well, you could say that then the DJL is 0 or something. CIK is 0 if K is greater than 1. DJL comes from the second table in the question, third table in the question, sorry. Do you have the question? Nobody has the question. Oh, Helen. So yeah, so it actually says in the caption of the table, it says this is DJL, the last table.
Might be a bit of a stupid. What's EIJ then?
EIJ is the benefit of relocating department I to location J, which is in the first table, which you don't have, unfortunately. Well, this is a nightmare. We're solving a question that nobody can see and remember. Okay, so what there was you've got 5 departments, okay, and 3 different cities, and you're deciding where to put each department. I'm putting department I to city J has benefit BIJ. So if you decide to put department, so this is the delta, if you decide to put department I to city J, you're getting this benefit. Okay, but then there's a cost of communication between any 2 departments, and the cost of communication between 2 departments is when you put department I to location J and department K to location L. And it's this, because this is the amount of communication between the 2 departments, and this is the cost per unit of communication between the 2 cities. So it's kind of complex in this sense that you don't just have, the cost of communication depends on 2 things. It depends on how much they communicate, and then where each of them is. Okay, and that gives you these 2 numbers. So you have to multiply them, and then you're only getting that cost if this is 1. So if actually you are putting I to city J and K to city L, and that's this gamma is supposed to signify exactly that. So these are the benefits of putting I to J, and these are the costs of communication between I and J if they're sitting in K. I and K if they're sitting in J and L. Okay. So that's the objective. Now you need some constraints. Right, so the first, somewhere in the question, it says that you must not have more than 3 departments in any single city. So that's quite easy to write. So you write that for every J, that's not a J, is it? For every J, being London, Bristol, Brighton, the sum of all the deltas I from A to E, for all the departments that go to J, can't be more than 3. Okay, no more than 3 departments. So there are, what does it say? Yeah, so this is just 3 constraints, and then there are only the kind of logical constraints. So first of them is that every department has to be somewhere, and in exactly one place. Okay, so this is quite a common one when the deltas. It's an what's it called? A disjoint set of possible options or something. But you have to select exactly one of them. Well, that's quite easy to do. So for all I, A up to E, so for all the departments, when you add all the deltas over all the J's, all the possible locations, then you should get exactly 1. And exactly one of them has to be 1, and the rest of them are zeros. And so that's that. But then, and then there are no more constraints really, except you want to enforce this gamma AJKL to be 1 exactly when these deltas are 1. So how do you do that?
What was it you said again?
Well, you want, you've got these gammas, plenty of gammas, and you want gamma with these indices to be 1 exactly when this delta is 1 and that delta is 1. And if one of these 2 deltas or both are 0, then you want that particular gamma to be 0. Okay? And you want to write it as a linear constraint. Of course, you could write it as a quadratic constraint. You could write that this gamma is equal to that times that. Okay, but that's a quadratic constraint, and you want a linear programming problem because that's easier to solve than a quadratic one. A little bit. Well, anyway, you want to express it as a linear constraint because that's always preferable. If you can write a linear model, then you're happier than if you can't. Sum it to 2. Not what?
Deltas.
So the gamma and the 2 deltas, no, I don't think you could. So what would you like to do? Gamma IJKL plus delta IJ plus delta KL should be 2.
No,
You don't need to write this. This is an attempt. This is Callum's attempt. So
no, I wasn't.
it doesn't look like anything.
I wasn't really including the first one.
You need the starts on the line. Just
We should move to a room with a bed, or a sofa or something, and you can have a nap.
I'm okay. I'm fine.
No, Helen. No.
Oh, Helen, definitely.
Why she keeps stressing me?
Don't write this down.
No,
This is just Callum's attempt.
No, what I was saying is
I'm gonna
the
create
gamma
a
is only
receipt.
1 when the sum of the deltas is 2. That's what I was saying.
Aha. But how do you write? I mean, what you want is a linear inequality or equality. Okay. You don't want any kind of if-then. I mean, it is if it expresses a sort of an if-then.
But it doesn't.
But you have to write it as a linear inequality
So you can't
or
say if.
equation.
You can't say if that equals.
No, you can't.
So it's,
I mean, you can do. You can say when you're doing your constraints, you can say if this and that, then add this constraint. But then this and that has to be a condition on the parameters on the data, not on the decision variable values. Okay, so you can say if the value of some parameter is non-zero, then we have this constraint. But you can't say if the value of this decision variable is non-zero, then we have this constraint. Constraints have to be there no matter what the decision variable values are. So, okay, so this doesn't work, does it? I don't know what this does even. It actually prevents the thing from happening. It sort of makes sure that we don't get that. So maybe
profit zero. Oh, that was also that time.
I think you can just set it onto like sense.
Oh, you forgot to put something as an integer or something?
What happened? You set it up to be.
No, no,
There's
no.
just something missing or something.
That is the first one. What's right? Boom, cost zero.
The program works. It just came with costs.
Came up with a solution.
Okay, so there's one thing. So you want to make sure that if one of the two deltas is zero, then the gamma is zero as well. Okay, so the way to make sure is that this happens is if you write gamma A, J, K, L is less than or equal to delta I, J, and also gamma I, J, K, L is less than or equal to delta K, L. And you add these for all I, J, K, L. I'm not going to say where they come from because you know that. But okay, so this is one. These two constraints or sets of constraints, they make sure that if one of these deltas is zero, then the gamma, the corresponding gamma also has to be zero. Now that's one thing. You also want to make sure that if they're both one, then that gamma is also one. Okay, and you do this by, I run out of page.
Squeeze it.
By saying that, that's true, delta ij plus delta kl is less than or equal to gamma ij kl plus 1. Okay. So these two constraints make sure that if one of the deltas is zero, the gamma must be zero. And this makes sure that if gamma is zero, then not both of them can be one. Which is both directions of that equivalent. In other words, if both deltas are 1, then gamma also has to be 1, because that sum is 2, and that also has to be 2. And then the last constraint is that all the decision variables
Wasting paper.
wasting paper, you know, this sort of it.
Big writing and then squeeze it.
Can't wait till after this. Like, why has he put vary? What does he mean vary? Enables. He's splitting it.
I'm not able to do it. Enables are binary. Oh my god. Oh my god. Yeah.
What?
No.
It's not me.
I know, but it's like intentionally for the
This is where he just does a giant arrow.
And so,
read list, yeah.
that's a high level making words, splitting words and stuff. Okay. Wasting. Any questions? Has everybody got the book? No.
Not with me, but
You have it?
Not a.
Is it inventory? I gave it out on Friday.
Oh, yeah.
So can you? We might have got it last year. So, but it doesn't matter. Okay, so we've got this. So what we're going to do is something more interesting than integer programming, or less interesting. Oh, yes, I would almost forget. So whoever's attempted this gets a chocolate.
wait.
So have you attempted, Mary, this question? Yes? At home? Did you get anything? Did you get the solution? Oh, you attempted. Who else attempted? Did you attempt? No. I attempted.
Depends what kind of sweets are.
It's Swiss chocolate with Swiss motifs on the cover. So yeah, well, maybe if the first years haven't attempted anything, then there will be some left next week. We'll see.
Technically.
Oh, it's not bad.
Oh.
It's quite good. Stop making. So now I'll pretend that I'm somebody else and I'll just read slide. Inventory theory is also known as.
This is going to be in the ISS. You're 1 out of 5.
Oh, yes. I completely forgot to give you feedback on your feedback. So I'll do that next week.
That's
Which
like
is
61.
no, it's not that I didn't forget, but I wanted to create a slide that I have to put on Moodle. And then I somehow ran out of time this morning because I thought, oh, I'm going to do it Monday morning. Oh, I'm going to do it Monday morning.
Oh crap, it's 12.
So, exactly. So, yeah, apologies. So, yes, but I'll solve. There wasn't anything really massive.
Yeah, just because you know my handwriting.
We know all our handwriting.
Yeah, so next time I'll bring typewriters.
I've actually done one.
Got a stamp. No.
So yeah, so I'll give you all those things next week. And for now, yeah, we're starting a new topic, which also exhibits itself in the fact that you've got a new booklet, which is a chapter from a book, just copied and plagiarized.
Maybe not a live stream.
I think the talks that you get for your projects should somehow be streamlined to avoid the question of plagiarism, because you're just using it against it. It's not plagiarism. I say this is a book. The Copyright and Policing Act allows me to copy up to 10% of any book that the library has purchased, and so this is it. Okay, so think of batch planning. Okay, do you remember the batch planning questions? That's a subset of this. Yeah. So in batch planning, we had these costs: inventory or stock holding costs, We had cost of setting up a batch or placing an order. It's the same situation. That's it. It's isomorphic. It doesn't know what isomorphic is.
I do.
And what we didn't have was a shortage cost, so we assumed that we never run out of stock. We cover all the demand in those models. So now we'll be looking at similar situations, and there might be situations where we run out of stock, and then there is a shortage cost associated with it. The output should be an ordering policy or a production policy. So whenever I'll be talking about ordering or producing, just think of them as equivalent. Okay, so either it's producing in a batch or it's ordering a batch of something, and there's always a fixed cost of setting up the batch or placing the order. That's this one, and it doesn't matter which of these situations it is because everything is just the same from the point of view of the maps that's going on there. And we'll be looking at two types of models. We'll start with deterministic, when you assume that you know everything, and then later on we'll move on to stochastic models where there's something random. Stochastic, the word stochastic means that there's some kind of randomness. But anyway, so it won't be totally random. We'll always assume that we know the probability distribution of the things that are happening. But, that will be a random component of things. So an example is this. It's a long example, but what it does is, okay, so example is silly sort of, you're manufacturing speakers for TV sets. And it's just a very simple situation. And the TVs are produced at a constant rate, 8,000 sets per month. And that's the consumption of the speakers. Okay, so someone, the demand is consuming 8,000 TV speakers per month at a continuous rate. Now, when you're producing the speakers, the cost of setting up the batch is 4,000. And the unit cost is £10 per speaker, no matter how many you produce. And then 30 pence per month is the cost of inventory. Questions? Common questions are often how much to produce and how often. Okay, so this is the same thing that we did in the first year. No, that's why I'm doing it again. If I thought you all remember, then I wouldn't be spending time on it. So I actually don't think anybody remembers. However, no, there's not there. Oh yeah. What was I going to do next? I think it's the assumptions. So let's try and solve this. Where have I spent all the time?
Trying to get the projector.
Tricky board.
I don't think it was the projector.
Yeah, do we not get it?
Oh, you haven't got a copy?
No.
That's why everyone's looking up like crazy. Sorry.
I didn't ask you before. I said I'm just going to speak projector like some people.
No, sorry about that.
Thank you. Oh, it's stable. Oh. Yes.
Yeah. Sorry about that. I completely forgot. Yeah, of course you get a copy.
You get a copy. You get a copy.
And I've left some space for you to solve it as well. Like notice. That was bad. Okay, so you've got a copy now, hopefully. I'm falling behind again. So the three assumptions, kind of following, it's also in the book. So demand is demand was constant, or the rate of demand was constant, I should try, but I forgot to write rate.
Well, yeah. I know.
Known and deterministic. Okay, so what does that mean? Constant means that it's the same all the time. We're producing the TV sets on a production line that is always running-ish. Okay, maybe ignore the weekends, but it's good enough to assume that it's the same every day, every hour, every second. Known means that it's known, and deterministic means that there is no random component. Okay. And the second assumption is that the order arrives or the batch is ready exactly when required. So we can also say that this is that we know the lead time. Do you remember what the lead time is? At the time between placing an order or initiating the batch and actually receiving the order. Oh no, you remember. So the lead time is what am I doing? Right. Yeah. That's the graph that's coming.
No, because you've replenished stocks.
Yeah. But there wasn't the one where it was like that. Directly. I seem to remember something like that.
It's just
Screen.
That's what I mean. Like, it would go up, down.
No.
Down.
Placing an order and receiving the goods. And that's lead time. And the third assumption is that plant shortages are not allowed. We're about 10% through this.
I'd like to take over Philip's collection and do the rest in that.
No. He's making a video now.
Oh,
No, but you want videos.
I thought you meant that it was going to close the
No, no.
please don't.
video. I'm not sure the video.
It's a pencil, it's like a factory one.
Okay, so what's the right way forward now?
To leave it here. We'll continue it next week.
Speed through it twice the pace.
I'll do it this way. So, theorem. Let D be the demand rate. So how much was it? D is, this is not part of the theorem. Okay, this is part of the example. K is the setup cost, so how much was it? £12,000 a batch. C, I don't want C. And H, stock holding cost. So in our example, H was 30 pence. Per unit per month. Then,
Wait, how about that other thing? The unit, the cost of the speaker is £10.
yeah, that's what I said, I don't want it.
Oh, you don't want it? Okay.
Then the optimal, because it's irrelevant, the optimal order quantity which is the same as the batch size of each batch or order is Q star, called Q star, perhaps, is equal to root of 2 times K D divided by H. This is the deal. So when you know what the setup cost is of each cost and what the demand rate is continuous, constant, deterministic, and known, and you know what the stock holding or inventory cost is, then you know that every batch of the speakers for every size of the order should be this much. Okay, so you can work it out in this problem, but you also know enough now to be able to solve the homework question. And next week we'll do the proof of this theorem or derivation of this formula. What's the size of the speakers? 25,000. Yeah, so you'd probably say 25,300 or something. Okay. Any questions at this moment? Yes. No. Yeah. This is the size of the batch that we'll derive next week. But now at least you have the formula, so you can plug in the numbers from a homework question and do that for next week and hope that there's some Swiss chocolate. Okay. See you later then.